Hi guys, my name is Amber Marsh and I'm going to be presenting my final project for ADTA 5560. In this project I'm going to be discussing the simple RNN model with sine wave data along with core concepts of LSTM cells. The first thing I'm going to be discussing is part 1 of the project, which is describing a data set. This dataset came from the Houston, Texas Police Department website. This file contains records for the year 2019 regarding criminal offenses in Houston given in a day, month, year format. This dataset that I will be talking about today has been filtered to only capture murders that have happened in Houston. The original dataset had multiple crimes, and that whole dataset had 2,856,519 data points. That included 219,35 total offenses for the year 2019. However, in this dataset, as I said before, I was filtering only by murder. So with this data set, there's going to be a total of 3,505 data points. As you can see and already noticed, this data is structured data and it is very organized and very easy to analyze. This data set has 14 columns that describes the details about crime that has occurred. These columns include incident, occurrence date, occurrence hour, class, description, offense count, beat, premise, block range, street name, street type, suffix, city, and zip code. As you can see in the description column, the only crime that we are focusing on is murder. If we look right next to the description of murder, we can see the offense count. If we go all the way down, we can see that the total amount of murders that have occurred in 2019 is 268. We can also see the time frame. We can see murders that happened in December, November, all the way through January. We can also see the residence where it happened, and even the street name and zip code. This would help if someone were wanting to identify a geographical location and if certain areas are more prone to murders. This data set can be very beneficial for anyone who wants to analyze murders that happened in Houston for the year 2019. There is so much valuable information that this data set could bring to anyone who is wanting to analyze it. It is very important to do exploratory data analysis before even starting your analysis procedures. As I was talking about before, it's very important to determine parameters, what type of data you are working with, how many items are in the data, and how you could potentially analyze it, solve it to solve for real-world problems. Now I will be discussing part 2, RNN, simple RNN with sine wave data. In this part, I'm going to create a sine wave data set, and I'm going to set all the parameters to generate the data set. I'm going to build it, train it, and evaluate it. I'm also going to make sure it has 2 layers involving simple RNN and a fully connected layer in Keras. I'm also going to determine how many neurons are used in the simple RNN layer. I'm going to present to you a diagram, and then I will present to you all the steps following that and give you my analysis at the end. So to begin with, I want to talk about the simple RNN diagram that we will be working with. As you can see on the left side, there are these pink circles. Each of these circles represent a neuron that's going to be in our model. As you can see, it goes 1, 2, 3, 4, all the way to 75. This is indicating that we have 75 neurons in our model. We can also see that all 75 of these neurons are going to go through this dense layer, which is labeled as 1. In this green circle, this represents another layer, so we can see that we have 2 layers total, one here and one here. We can then see that after our neurons went through this dense layer, we are then able to get to our final output, which you can see right here is designated by a purple rectangle. So the first thing we do is we have to build the model. To build the model, we first have to do basic things such as importing Python libraries. This includes import pandas as PD, import numpy as np, matplotlib npline, import matplotlib plyplot as plot. Also from TensorFlow, we got to import keras. From tensorflow.keras, we have to import layers. We also need from tensorflow.keras to import sequential. From tensorflow.keras.layers, we have to import simple RNN. From tensorflow.keras.layers, we have to import dense. We also have to import TensorFlow keras preprocessing sequence to import the time series generator. And finally, we need to use from sklearn preprocessing to import the min-max scaler. But we also need to specify how we're going to set it up. So in this example, we know that it has 2 layers, and we need to explain that range. So the range, it's going to go 0 to 100, which is shown here by line space. Then we're going to divide that range by 1,250 data points. We're doing this because we're splitting it into training and testing model to make sure we get the most accurate results. We can also see in the graph below, we can use this to verify that we correctly identified that this is sine. We can see that y is a function of sine based off the waves that it is producing. That's going up and down, up and down. And we can see our range, which is going from 0 to 100 on the x-axis. So after we do this, we need to split our data. Splitting our data is very important to go into training and testing splits. So in our original data set, like you've seen before, we have 1,250 data points. We want to split this into a 20% and 20% and 80% split. So to do this, we would multiply 1,250 by 0.2 to get this number. And then we're going to subtract this number to get the rest, which is 1,000. After this, we are finally able to build our simple RNN model. After this, we need to define features and compile the model. As you can see right here, there is 75 next to simple RNN. That represents 75 neurons that are going to be in our model. We can also see right here this dense 1. That is the 1 layer that we're adding to our model. This is represented in the diagram that I showed you earlier, which we can go back to. As you can see, the pink represents the 75 neurons. This green represents the dense layer. So these 2 layers will then give us an output. So after we do that, we can compile the model. As you can see in the bottom right, this is the result we get. We can see a shape. So with the simple RNN, using the 75 neurons, we got a parameter of 5,775. With the dense layer, we only got a parameter of 76. So after this, we're able to train and fit the model. To train the model, we're going to go into this function, and there's going to be 5 epochs. Each one, after it runs, you can see there is a loss. If you look to the right, we're visualizing the performance. This graph is showing our loss over time. So you can see that it goes down significantly at 1, and then it fairly stays a straight line until about 3, and then it goes down again. This is just indicating how much of a loss we are producing. So after that, we can finally evaluate our model. By using specific code, we are able to put our sign column and our prediction column next to our attributes. So as you can see, the first is 80.06. The sign of that was negative 0.998, and the prediction that our model created was negative 0.997. That is a very close prediction and does very well. But if we look at the bottom, this value is 100. The sign was negative 0.506, but the prediction was negative 0.432. It's still pretty accurate, however, there is a little bit that's off. And to more accurately see that, we can plot it. So a better way to show this instead of a table is a graph. So on the right, you can see that sign is blue and predictions are orange. In the beginning, the predictions are very close to the sign values, but except for the peaks and troughs, there are a little bit of gaps, which show that it's not doing it perfectly, predicting it perfectly. But then you can see once it hits about 91 or 92 on the very right, it gets very off. So this just shows us that although our predictions are very good in the beginning, it might not be a good model to use if you're wanting to use it for further values down the road. The next thing I'm going to talk about is part 3, LSTM cells core concepts. LSTM stands for long short-term memory. As you can see in the figure below, the figure on the right represents an RNN cell, and the figure on the left represents the LSTM cell. You can see that the one on the left is far more complicated than the one on the right. So the first thing to discuss is this RNN model and what is happening. You can see that there are inputs. This X is an input. This right here is a hidden layer, and then it goes to this activation function, which results in an output. So on the left model, it's basically doing the same thing, but there's more stuff happening in the hidden layer. If I show you this image, you can see that C is what we're focusing on, and it is a straight line. It goes straight forward. But all the other stuff that's happening behind the scenes is a hidden layer. So knowing that this is a hidden layer allows us to understand what actually is happening. So this cell allows it to learn over multiple steps. This has both cells, states, and gates, and they both work together to perform memory functions better. LSTM stands for long short-term memory, in which the RNN model does not have. RNN model struggles with short-term memory, and this one allows us to have memory for a longer time. The model is able to do this and store more memory because there is no weight involved in the layers. There's multiple functions that allow us to solve this vanishing gradient problem, which allows this to be a better cell to use if possible. Like I said before, this cell has both cells and gates. There are three gates. It's the forget gate, the input gate, and the output gate. The forget gate decides what information of the previous cell should be kept or removed. If it is removed, that means the information is irrelevant to what is being analyzed. But if it is kept, that means the information is significant and needs to stay. The input gate decides what inputs are useful and if they should be added to the new cell state. This function is called a save vector and shows what useful information that has been kept. This will then become part of the new current cell state. Then the output gate computes and extracts the new current cell state from the previous functions. After this, it decides what information should be used to make the new current hidden state. These outputs are usually a vector called focus that represent the current hidden state. So all in all these gates and all these cells are correlating and bringing it back to the C line. Because of this, there's no weights attached to this, and it can go in a straight line, which allows us to have more memory and can perform much better when remembering more data or tasks. Now I will be discussing part 4, LSTM with time series data. In this part, I will be creating a time series data set that has only one numeric attribute. I am able to pre-process this original data set to achieve this if needed. I'm also going to design the network and decide the values of relevant parameters. I will be discussing the percentage of data for testing, how many layers of the long short-term memory, how many number of neurons in each long short-term memory layer, if there are any dropout layers, if there are or is a dropout layer, the percentage to drop. I'm also going to talk about the length of the time series input sequence, the batch size, as well as the number of epochs for training. I'm going to build this LSTM neural network using the Keras sequential model. I am then going to train the model using the training data part of the collected data set. I'm going to test this model using the testing data that has been allocated from the collected data set. I am then going to retrain the model using the whole collected data set and prepare it for forecasting. After that, I will perform the forecasting and then run all the steps to perform my analysis. The data set that I'm going to be using is weather, specifically the high temperatures from 1953 to 1955. So the first thing, like we did in the other model, is you have to import important libraries and upload the data set. So these libraries that we're going to import to Python are import pandas as PD, import numpy as np, matplotlib inline, import matplotlib.plyplot as plot. Then from tensorflow.keras.models, we're going to import sequential. From tensorflow.keras.layers, we're going to import LSTM. From tensorflow.keras.layers, we're going to import dropout. From tensorflow.keras.layers, we're going to import dense. Then we're also, from tensorflow.keras.preprocessing, we're going to sequence, import, time series generator. Then we're also going to use from sklearn.preprocessing to import the min-max scaler. After that, you're able to see what exactly is in the data set, and then you can filter from there. So as you can see on the bottom, there are columns with the date and Tmax. Tmax stands for the max temperature, and we only want that column. So we're going to filter everything out and only get that column for our analysis. We can also do EDA, which explores the data even further. We can see the shape, we can see what type of variables are used, and we can also see statistics such as mean, standard deviation, and so on. We can also see a graph of this. As you can see, it's going up and down, which indicates that it gets hotter in the summer and colder in the winter, which would make sense. The next step in this process is we're going to split the data, normalize it, and then use time series generator. Splitting the data is very important, and we did it in our last model. We're going to split it into two sections. One will be train and one will be test. To do this, we're going to use a 2% split rate on our whole data set. We're going to multiply 0.02 by our total amount of records, which is 1,095. As you can see, this is what we'll get at the very top, 219. Then we're going to subtract that from our total to get our other part, which would be a total of 876. After that, we can normalize the data. This is converting it to a 0 to 1 range. We use scalar, we use min-max scalar, and this will scale both the train set and the test set. After this, we're going to create a time series generator for our training. As you can see in the code below, we're going to specify that the batch size is 25, and to train the TS time series generator 40 to the normalized training set. After this, we're going to build and compile our long short-term memory model. To do this, we're basically just setting the parameters and including what everything is. As you can see on the left, the number of features is going to be 1. We then will have to define the model, which is sequential, and then we're going to add LSTM layers. To do this, we use an activation function of RULU, and you can see that that is going to be 55 units. After that, we can continue to add layers, and we're also going to add a dropout layer in our model. In this example, our dropout layer is 0.25, which is going to be 25%. And then you can also see that our dense layer is 1. So after we define all the attributes on the left, we're done building, and now we need to compile the model. As you can see on the right, to do this, we have to use both an optimizer and loss function. These are very important when defining the model. For loss, we're going to use MSE, which stands for mean squared errors. This is because our data is continuous and will have the most efficient results. For the optimizer parameter, we're going to use ATOM. This is a very popular training model to use when we're compiling the function. Once we run this code, we are able to see the following output. As you can see on the left, there are multiple layers. There's LSTM, dropout, LSTM, dropout, LSTM, and dense. This is a total of 6 layers. There's 3 LSTMs, 2 dropout layers, and 1 dense layer. You can see the output shape, the number of parameters it produced, and then at the very bottom we can see that there are 61,436 total parameters. Now after this is done, we can visualize the prediction. This on the left is showing a table of the predictions being made. On the right, we can see it in graph form. You can see that blue stands for the temperature that's recorded, and the orange stands for the prediction. You can see it matches up pretty perfectly, and it's a great model so far. So after that, we're able to build a new model for our new data set. This data is for the year 1956, and it's going to see if we can forecast the model correctly using the model we already created. So to retrain the model, we're going to build and compile the same thing like we did last time, and we're going to use Model Fit Generator and 45 EPCOTs. After this, we need to transform the data. This is very important to define that there are 219 periods, and we need to transform or normalize the data back into its true values so we can see and compare the accurate results. We then have to create a new timestamp index with pandas, and this is just defining the range, 876 to 1095. It's the same thing that we saw in the very beginning. Now we're able to forecast using the new data. As you can see on the left, there are two columns now. One is the temperature max, and on the right is the forecast that we just created using the code. You can see that it's very close, but it's not 100% accurate. You can see in the first column, the real value is 62 and it forecasted 59.5. Then you can see at the very bottom, the temperature was 88, but it forecasted 90. So it's a pretty good model, but it is not a perfect fit. You can even see this on the right when we visualize it into a graph. You can see that the blue represents the true values and the orange represents the forecast. You can see that we trained it very well to represent the trend in the data, and you can see visually that being performed. So in conclusion, I think this is a very accurate model and I personally would use it. We tested it and trained it very well to predict and forecast future values for 1956 weather. Although, as we discussed earlier, it isn't 100% accurate, I believe it does a very good job at predicting the values, considering that the summer months are hotter than the winter months, and you can see that dip go down and then it goes back up. I'm sure if we trained and test the model again with new parameters, I believe that we could probably get even more accurate results.